Hello, everyone. Hope you're doing well. Let's do a little bit of practice here with some things with normed vector spaces. Using some examples that we have been learning are examples of normed vector spaces and showing how we can kind of navigate through these in interesting ways and discover a few things about what these norms do and how all of these different norms operate in relation to each other as well. So we'll go through a few questions. This first question here talks about comparing the different norms that we've been talking about. It turns out that there is a strict less than or equal to inequality relation between these norms that we've been looking at for the 1, 2, and the infinity norms. And the second one is going to involve the operator norm. Once again, getting used to matrices having some norms as well. We find the operator norm in our video lecture for section 8-1. So we'll try and use it here in question 2. So let's just get used to some of these examples with norm vector spaces and the types of questions that we might study in relation to these. So starting with this one, first we're going to take a vector inside of the space of little L1, and we're going to show that the norms of the vectors x with respect to the infinity, 2, and 1 norm have a less than or equal to relationship between the 3 different norms. So we'll want to show this in 2 parts. The first step we're going to want to show is that we can take the infinity norm of a sequence like x. By the way, we'll keep calling x the sequence of x of n here. And we're going to show first that if this is a less than or equal to the 2 norm of this sequence. Now, kind of looking at these 2 things, it seems like it would be difficult to think about why one thing might be less than or equal to another. The one that's up here on top says, take what is essentially the greatest element of a sequence, or if there isn't a greatest, take the least upper bound of that sequence and to find that to be the norm of it. And then the second one says, don't just take one greatest element, take all of the elements, square them, add them together, and then take their square root. Although that comparison does sound like there's a little bit of a less than or equal to thing here. This one seems to care about one element while this cares about many elements and how they work. So let's see if we can start trying to break that apart in a more formal proof here. First, let's define what it means to be the infinity norm. Note that this supremum signifies that we may not necessarily have a maximum element inside of this sequence. It may only be a supremum. That means that there is going to be some element n in the natural numbers and some element of the sequence that corresponds to x of n, such that, and then this will be for all epsilon greater than 0. I'll go ahead and say this here, such that the norm of x infinity minus epsilon is less than this x of n value, at least in absolute value, is less than the norm of x. So this, remember, is something that gets involved here with working in the supremum world, which is that we don't necessarily know if there is an absolute value of x of n that equals this norm. I'm thinking of sequences like 1 minus 1 over n, which go 0, 1/2, 2/3, 3/4, that have a supremum of 1, but don't ever have a sequence element that reaches 1. But 1 is still the supremum because it is the least upper bound. You could think of it as like this is an increasing sequence, and this is where they approach. Another way to say that is that if you went to any number that was a little bit less than that least upper bound, less than 1, like in that example, then you could still find a sequence element that was greater than. But of course, it must still be less than or equal to the least upper bound. Otherwise, yeah, it wouldn't really be an upper bound at all. There would be a sequence element that'd be greater than it. But it is the least upper bound, so this does not get to work as a least upper bound. So there is a sequence element greater than it. So for all epsilon greater than 0, there exists this n. What can we say about this then? Note that the norm of x infinity minus epsilon, we know this to be less than the absolute value of x of n, that this is equal to the x of n squared to the power of 1/2. Now, why would I write it like this? This is something that's certainly true, but what I'm doing is I'm trying to make a connection here between what I'm trying to use for the infinity norm and what I see a lot of here in the 2 norm. That seems to be something that helps connect these two things. In particular, when I see that I'm squaring x sub n, I don't need these absolute values anymore. It's just x sub n quantity squared to the power of 1/2. Now, if I'm trying to say that this is going to be less than or equal to the 2 norm, then something that I might try to do is try and write out what this looks like here. So this is going to be the sum, as n goes from 1 to infinity, of x sub n squared, all to the power of 1/2. Now, let's take a look at these two things and start doing a bit of comparison. Taking a look at what I have up on this line right here and what I have on this line right down here, it looks like I have something that is less than or equal to by observation. So it looks like I did a very good thing here. So how am I saying this less than or equal to? This is a sum of many squared terms of x sub n. In fact, maybe I should actually go through and call these x sub k squared so that I am not confusing that with this n that is a fixed variable and a fixed index for my sequence. And k is an index that's allowed to change in range over the entire sequence. And I am adding over all of the different elements here for what x sub k squared is. So this is going to include both the n value that is inside of the sequence, this x sub n here, and it's going to include even more. So this is a less than or equal to by the fact that the square root is an increasing function. If I kept adding bigger and bigger terms inside of the square root, then the square root itself is going to grow. It's going to increase. So this is absolutely a less than or equal to. And if I wanted to give a explanation for this, this last inequality is because x sub n squared is less than or equal to the sum as k goes from 1 to infinity of x sub k squared, and the square root function is increasing. This is true for all epsilon. I haven't forgotten about that epsilon that we had from above here. We haven't quite shown that indeed that the norm of x infinity is less than or equal to the norm of x2. But analysts use this trick a good bit. If you get to show that this is true for all epsilon, then you can let epsilon go to 0. What does that mean? Take epsilon to be something like 1 over m or something like this. And note that whatever this epsilon is, as long as it's something greater than 0, this inequality remains true. Then let m continue to grow higher and higher and higher. Because this inequality holds true for all of these values, it has to hold true for the limit. Let me kind of give that as a comparison based on our previous idea. Let's say that you have the value of 1 minus 1 over n, and you know that this value is less than or equal to 1. Well, if I know that this is true for all n in the natural numbers, which is indeed true, then I can actually claim that 1 is less than or equal to 1, because as I continue to make this smaller, I'll have 1/2 is less than or equal to 1, 2/3 is less than or equal to 1, 3/4 is less than or equal to 1, 4/5 is less than or equal to 1. There's no way that at some point, as I keep going through the sequence, somehow the limit makes a jump in the inequality. 1 is not going to be strictly greater than 1, because the thing is that the sequence converges to this point and we have no holes in our space. So actually we do get that this ends up working neatly, that this 1 is not greater than 1, that it is less than or equal to 1. So that's the concept that's being illustrated here. We are letting epsilon go to 0 to say that in fact, this shows that the norm of x infinity is less than or equal to the norm of x2. Now, even though we have a strict less than there, taking the epsilon go to 0 doesn't give us, kind of like in that last example, it doesn't give us strict less than inequality. It gives us less than or equal to. We have to be ready for that. But that is essentially a limit comparison test idea that allows us to allow the epsilon to go towards 0. And that gets us the first step. All right. So let's keep going. And now let's show that, in fact, that the norm x sub 2 is less than or equal to the norm x sub 1. So what we would want to show now is that the sum as k goes from 1 to infinity of x sub k squared to the 1/2 is less than or equal to the sum of k goes from 1 to infinity of the absolute value of x sub k. So let's see if this is something that we can hold true. Well, let's work backwards. If we wanted this to be true, this less than or equal to be true, what could we try to do to make that a little bit more clear? How about we get rid of any of our root functions? Let's see if it's a little bit easier to claim this if we say that the sum as k goes from 1 to infinity of x of k squared is less than or equal to the sum as k equals 1 to infinity of the absolute value of x of k quantity squared. So a few things here. One thing is it's automatically fine for me to put absolute values around these x of k so that the absolute values don't end up quite scaring me too much. But let's take a look to see if we can justify to ourselves that this less than or equals to is true. Well, we have something that we've called the distributive property in the past, that if you have a bunch of things being added together and you square them, then one thing that's going to happen is you're going to take x of 1 plus x of 2 plus x of 3, so on and so forth, and you're going to multiply that times absolute value of x of 1 plus absolute value of x of 2 plus absolute value of x of 3 plus dot, dot, dot. And doing that multiplication, at some point, you're going to be multiplying times the elements themselves as you distribute these things. But take a look at what those products are. Those products are absolute value of x of 1 squared, and x of 2 squared, and x of 3 squared. And as you go through and add these together, you're going to get these terms as you go through and solve this problem. What's more, you get more than that, because I didn't even include the fact that you could be multiplying x1 times x2, or x2 times x1, or x2 times x3, or x3 times x2, so on and so forth. There's a lot more that's being multiplied on the right-hand side. Notably, more positive terms are being multiplied on the right-hand side when I square the entire sum. Note how order of operations kind of told us that there's a difference going on here. Here, this says take the numbers, square them, then add them. This says take the numbers, add them, and then square them. And that makes a big difference in what we get. We get a less than or equal to from that inequality. So that is true because of how the distributive property works. Now we can go backwards. This is absolutely true. So now we can take square roots of both sides and we are done. So a way that we might try and write that out is something like this. Note that 0 is greater than or equal to the sum as I is not equal to j of x of I times x of j for I and j in the natural numbers, which implies that the sum k goes from 1 to n of x of k quantity squared. What that does is that adds back in all of the places in which you're squaring x of I. So that's going to be x of I times x of I, where in this case I is equal to j. And what you're going to be getting there is the sum as I and j in the natural numbers, multiply x of I, x of j. But this is exactly the definition of summing x of k as k goes from 1 to n and quantity squared. So this will be a less than or equal to here, actually. There we go. And then this will imply that we can now take square roots of both sides. So we can now take the sum as k goes from 1 to infinity of x of k squared to the 1/2, which we know is equal to the 2 norm of the sequence, is less than or equal to the sum of k goes from 1 to infinity of absolute value of x of k, which is equal to the 1 norm of that sequence. Pretty neat stuff. So that would be like a more formal way to write that. What it does is it says, I'm starting with something that I can say is true because I'm summing a bunch of positive numbers together, and hence that has to be greater than or equal to 0. Then I'm just going to add the same thing to both sides, namely those terms that are squared, and that's going to be the same on that side, adding a little bit more to that sum, making it so that it's all possible I and j in those indices that I write it there. And that can be itself rewritten in a way that looks like my norm x1. But the way that we got there was definitely not by just pulling that out of thin air. It was from kind of trying to work backwards a little bit. Of course, this is a very good type of proof for what we have going on in this class. You can just try experimenting with these kinds of forward proofs, if you would like, as we keep moving forward in the class. So let's keep going here and take a look here at question 2. Now let's remember that the operator on this norm of the n by n matrices is something we talked about back in the video lectures for 8-1. And that norm looks like this. It is equal to the supremum over for all vectors inside of X or x vectors inside of the space that we're looking at, which would be r to the n, such that the norm of x is equal to 1 of the values of a times the vector x. So let's first talk through this a little bit more, make sure we understand kind of what's going on here. The idea is if you look at a matrix, and if you start with all of the elements that have a norm of 1 inside of Rn, here I'm drawing a picture of what the elements of norm 1 would be for the real numbers. And that looks like the unit circle. What mapping that unit circle through the matrix A does is that sometimes it will deform it a little bit. It'll stretch it out a little bit more, show you that you can take a vector inside of this spot and maybe have it stretch in this direction. Maybe that involves something like eigenvalues to tell you that if I take this vector and I can stretch it by a factor of 2, then that's exactly what's happening here to this part of the unit circle. This is something that I describe for my students when going through and talking about eigenvalues in 632. But what are we going to do now with this notion of taking the supremum over all vectors x of the norm a times x? Well, what's happening is this vector here that I'm working with is the vector x. As I map it through A, what I end up getting is the vector ax. And what I'd like to see is what is the distance that that function takes if I know that everything that I started with had distance 1, starting from the unit circle. What's the farthest distance that that can stretch? Can it stretch by a factor of 2? Can it stretch by a factor of 3? It's notable here that we said that the norm of this a sub a times x is equal to the absolute value, the square root of the lambda max, which is the greatest eigenvalue in magnitude of the matrix A transpose A. Because you can see here why maybe the eigenvalues get a little bit connected in there. And we'll explore that a little bit here in a homework problem dealing with some of these operator norms, which is that the stretching that goes on as you move from one space to another is something that can help impact this operator norm. But we are going to talk a little bit differently here with this problem. We're going to show that the norm of A times B is less than or equal to the norm of A times the norm of B. And let's take that same type of process that we did last time and try and work backwards for this one, using this as our way of describing this. Let's first take and rewrite the norm of A times B. Well, the way we're going to do that is we're going to take the supremum over all vectors in Rn and have a norm equal to 1 inside of that space. And we're going to ask if this is less than or equal to the supremum over all, and I'm going to use a different vector here, supremum over all y vectors in Rn, such that its 2 norm is equal to 1 times the vector ay. Oops, forgot to write what I was trying to actually take the supremum of on the left-hand side. Allow me to go back and do that. And so that should be of the norm of the matrix A times B. And where that's going to fit is we're going to take a look at what this is. This is the norm of A, and we're replacing the norm of A with AB. So what gets replaced here inside of this definition is A times B times the vector X, something like this. And this is we're going to ask if this is less than or equal to the norm of A. Here I'm using y to kind of distinguish it from x to say that those could be different vectors, times the supremum over all z in Rn, such that the norm of z is equal to 1 of b times z. And I want to see if there is a way to be able to determine if this is true. So let's see if that is possible. So let's start like this. I want to find a way to basically break these things apart. This a times bx and things like this. Well, so let's see if we can find a way to make that work. How about this? First, we know that the norm that b times x is going to give us another vector. That other vector is something that we could be plugging in x. So let's start with let x be in Rn such that the norm of x sub 2 is equal to 1. Then bx, whatever this vector is a vector in Rn. I'll just go through and try and make that as a specific thing. What I mean by trying to specify that as a vector is that it is something that I could go through and then plug into A. And perhaps Bx is my vector that gives me my supremum, the vector that helps me achieve my norm. So that is a candidate here in the world of things that allow me to have a supremum. So I'm going to go ahead and mention that B times the vector x is a vector inside of R to the n, because I'm about to use that in a particular way. Note that Bx is less than or equal to the supremum of, let's see how I want to write this here. I would like to write it like, I had to think about that one for a little bit so that I can make sure that I made it fit the definition that we are using for operator norm. And that definition says, if I'm trying to compare it to something that looks like a norm, then I need something that is a unit vector. So note that Bx divided by the magnitude of this Bx is a unit vector in the direction. This is the 2 norm. And then the direction of the vector Bx. And we also have what? That if we take and plug this in here into the matrix A, that the norm of A times this Bx divided by Bx 2 norm, that now I am plugging in a unit vector in for A, a vector that I don't really know much about, but I do know that it is less than or equal to the supremum over all vectors in Rn, such that its norm is equal to 1 of the vectors. I should now use the letter y that I was using up above, of the matrix A times the vector y. Now, how do I know this? Take a look at this. This is a unit vector that is inside of Rn, and that has its 1 norm, or 2 norm, should say, equal to 1. Because I've gone through and divided by its norm, it's now a unit vector, so its 2 norm is equal to 1. So now I can start using this as like, okay, this is one of the candidates of the vectors of what I could be plugging in for the matrix A to help me find the operator norm for this. So I'm using this supremum idea of saying that if I have a vector I could plug in, it's definitely less than or equal to the supremum of it, definitely less than or equal to the max. When you see it that way, it becomes a little bit just obvious almost. It's not immediate as when you first see it why this is the case, but think of it like this. What I'm doing when I plug this in is that I am taking a vector that is of norm 1 and plugging it in for A. That's definitely going to be less than or equal to the supremum over all of those norms of norm 1 vectors when plugged in for the matrix A. But this inequality is exactly everything that I want. So let me see if I can show you why. Because I can start playing around with this idea a little bit more. So let's see if I can lasso this guy up and then show you that a little bit. That's going to get us everywhere that we would like to be. Whee! Perfect. Awesome. So let's see that here. First, this right here, just to be clear, this is the norm of A. So that's what this is. So whatever the norm of this vector is equal to the norm of A. Now I can move around things inside of here for free. This is a scalar down here. So if I divide by 2 inside of one part of the fraction, I could just be dividing by 2 on the inside right over here. This is 1 bx of 2 times A times B times the vector x right over here. So I know that this is less than or equal to the norm of A by implication of just me being able to move this from underneath b sub b times x to be its own scalar fraction. So what I'm doing there is saying, okay, well, this part is just like 1 over 5 or 1 over 10. It's a scalar number, and so I can move it anywhere inside of the norm. But notice something else I can do with scalars. I can also move it outside of the norm. So I could say that this is 1 over b times the vector x sub 2 times a bx. These are all 2 norms here, by the way. And that's less than or equal to the norm of A. Then I can go a little bit farther, and I can get everything kind of rid of in terms of a fraction. And what I'm left with is that the 2 norm of ABX is less than or equal to the norm of A times the norm of B sub x2. So this here, just to be clear, this is the operator norm that I'm using here. This is the operator norm of M sub n R. And I could keep doing that throughout each of these just to make it so that it's distinguished from my other norm. Something like this. And this is where I've gotten so far. This is me just using properties of the norm to bring a scalar value outside of the norm and then multiply it across to get this inequality. Now, how close are we? We're pretty close. What we would like to say from this point is that the norm of A times B is less than or equal to the norm of A times the norm of B. Well, you may have seen this before. We've done this back in week 2 when we were talking about supremum and infimum of sequences. It is okay if you have that A is less than or equal to B, then the supremum of A is less than or equal to the supremum of B. So take supremums over all vectors x such that the norm of the vector x is equal to 1 on both sides. And that's something that we are allowed to do. We saw that back with sequences. We saw that back with sets back a ways back, but we're actually getting to see that here. So we can now write that this is the supremum for all vectors x in Rn, such that the norm of the vector x is equal to 1 of this vector a b x sub 2 is less than or equal to, this is just a scalar, so we can bring it outside this supremum, x of Rn, such that the norm of x sub 2 is equal to 1 of the vectors b times vector x sub 2. And finally, these are the definitions of the operator norms. Here, this is a times b is less or equal to the norm of a times the norm of b. Notice that that takes a little bit of time. There's a lot kind of going on and a lot of supremums and things like that to work with. But I want us to see here that this is a neat property that we're going to be working with a little bit in week 9. And so I want us to see how that proof works before we start using it very frequently as something to be using in the future. So that's where I wanted to show it happen, is with this notion of an operator norm. Because here I'm calling it as an operator norm. In a previous video, I mentioned operator theory. You better believe that this is the sort of thing that we want to be talking about for elements inside of week 9. So the idea here was, just to kind of summarize for this last part, we took a times b sub x and thought of it as take a vector and let's show that we could take something that's a unit vector in a specific direction and get it to be a less than or equal to the operator norm for that matrix A. This is true for an arbitrary vector x, so I can take a supremum, and that supremum is good enough to show me that I can get that a times b's operator norm is less than or equal to the norm of a times the norm of b. Now, there's definitely a lot of math in that, and I want you to kind of look through this and start becoming a bit more familiar with this type of stuff. Whatever your final project might be, you might be going down this direction, seeing things in this sort of realm. So it's better that we see a little bit more of it now and then try and continue to make sense of it as we move along. But that will do it for us today to see how these two questions work together, working together with normed vector spaces. First, how we can do things with little l1, and then also how we can be doing things with norms and matrices and using these ideas together. The ideas behind them may seem like these are completely new, but honestly, these notions, very many of them, stem back from expanding out using the distributive property or knowing what a supremum might do for a collection of numbers, coming back to what we saw back in homework 2 for that one. So once we see it as such, and that we're just adding a few more definitions here to collect things and make things work for these norm vector spaces, we'll be able to start separating out and dissecting other long and complicated proofs and start understanding a bit more about why the world of mathematics works the way that it does. But that'll do it for me today. Thank you so much. Have a wonderful day.